Scientists have spent many years looking for signs of life beyond Earth. They built the most expensive telescope in history. They pointed it at a world that is 8 times the mass of Earth, and they found something. A chemical fingerprint that on Earth comes from living things. The statistical confidence is 99.7%. If this detection is confirmed, everything changes. This is the story of the molecule that may prove we are not alone. But before we begin, do not forget to subscribe. And if you truly enjoy these videos, please leave a like. Let us begin. What you are about to hear is not speculation. It is not science fiction dressed up as a documentary. It is a story about a signal, a molecule, and a question that humanity has asked since the first person looked up at the night sky and wondered if we were alone. The answer may have arrived. Not with a radio transmission, not with a spacecraft landing on our planet, but with light. Ancient light from a world 120 light-years away, filtered through an atmosphere that should not contain what it contains. Unless something is alive there, unless something is breathing, metabolizing, existing in ways we barely understand. This is the story of Kate 28 billion. This is the story of dimethyl sulfide. This is the story of how we might have found proof that life exists beyond Earth. And this is the story of what happens next. Chapter 1. The Signal. September 2023. A room full of scientists stares at data on screens. The James Webb Space Telescope, the most powerful eye humanity has ever built, has been watching a distant world for months. Not watching in the way you or I might watch something, watching by collecting photons, ancient particles of light that left a planet called Kate 118 billion more than a century ago. These photons have traveled across the void at 186,000 miles per second. They have crossed interstellar space, dodged dust clouds, survived the journey through our own solar system, and finally, after 120 years of traveling, they have landed on a mirror made of gold and beryllium floating at a point in space called Lagrange 2, about 1 million miles from Earth. The telescope does not see the planet directly, not really. What it sees is the star that the planet orbits, a red dwarf called Kate 118. And when the planet passes between that star and us, something remarkable happens. A tiny fraction of the starlight passes through the planet's atmosphere before continuing on to the telescope. That light carries information, chemical fingerprints, absorption lines that tell us what molecules exist in that alien sky. The scientists have been analyzing these fingerprints for weeks. They expected to find methane. They expected to find carbon dioxide. Both are present, but there is something else. A signal that does not belong. A molecular signature that on Earth has only one source: life. The molecule is called dimethyl sulfide, DMS. 2 carbon atoms, 6 hydrogen atoms, 1 sulfur atom. A simple compound by the standards of organic chemistry. And yet, its presence in the atmosphere of Kate 28 billion changes everything. Because on our planet, dimethyl sulfide is produced almost exclusively by living organisms. Phytoplankton in the ocean, bacteria in the soil, algae floating on the surface of ponds. These microscopic creatures release DMS as a byproduct of their metabolism. It drifts up into our atmosphere, where it plays a role in cloud formation and climate regulation. Without life, there would be no dimethyl sulfide in Earth's air. And now, 120 light-years away, the same molecule appears to be floating in the hydrogen-rich atmosphere of a world more than 8 times the mass of Earth. The statistical confidence is 99.7%. That is not certainty. That is not absolute proof. But it is close. It is close enough that the scientists who made this discovery cannot sleep. It is close enough that papers are being written, peer reviews are being conducted, and telescopes around the world are being pointed at this one spot in the constellation Leo. Because if this signal is real, if dimethyl sulfide truly exists on Kate 118 billion, then we are not alone. We have never been alone. And the universe is far stranger and more alive than we ever dared to imagine. But let us not rush. Let us take our time with this story, because the journey to this moment has been long, the implications are vast, and the questions that remain unanswered deserve our attention as much as the questions that may have been answered. The story begins not in 2023, but in 2015. That year, a space telescope called Kepler was nearing the end of its primary mission. Kepler had been launched in 2009 with a simple but audacious goal: find planets orbiting other stars, not by seeing them directly, but by detecting the tiny dimming that occurs when a planet passes in front of its star. This technique is called the transit method, and it has revolutionized our understanding of the galaxy. Before Kepler, we knew of a few hundred exoplanets. After Kepler, we knew of thousands. The telescope stared at a single patch of sky for years, watching 150,000 stars, waiting for the telltale dip in brightness that would indicate a world crossing in front of its sun. And in that data, buried among the noise and the false positives and the binary stars, was Kate 118 billion. The planet was discovered by a team led by scientists at the University of Montreal. They noticed that the red dwarf star Kate 118 dimmed slightly every 33 days. The dimming was consistent, repeatable, the signature of a planet in orbit. Initial calculations suggested a world about 2.12 times the radius of Earth. Further observations refined the mass to approximately 8.6 Earth masses. This placed Kate 28 billion in a category of planets we call sub-Neptunes, larger than Earth, smaller than Neptune. Common in the galaxy, yet absent from our own solar system. The planet orbits its star at a distance of about 14 million miles. That sounds close. Dangerously close, perhaps, if you're thinking of our own sun. But Kate 118 is not like our sun. It is a red dwarf, a star far cooler and dimmer than the yellow star that warms our world. At 14 million miles, Kate 118 billion receives about the same amount of energy that Earth receives from the sun. It sits in what astronomers call the habitable zone, the region around a star where liquid water could theoretically exist on a planet's surface. For years after its discovery, Kate 28 billion remained one planet among many. Interesting, certainly worth noting in the catalogs, but not yet special. The James Webb Space Telescope changed that. When JWST launched on Christmas Day 2021, scientists around the world submitted proposals for observation time. The telescope could only look at so many things. Competition for access was fierce. Kate 118 billion made the list because of its unique combination of characteristics. It was large enough that its atmosphere could be studied during transits. It was close enough that the signal would be strong. And it was in the habitable zone, meaning any discoveries about its atmosphere could have profound implications for the search for life. The observations began in 2023. JWST trained its instruments on the Kate 118 system, waiting for the planet to cross in front of its star. When it did, the telescope collected the light that had passed through the planet's atmosphere. Spectrographs broke that light into its component wavelengths, and scientists began the painstaking work of interpretation. The first results were exciting, but not shocking. Methane was present. Carbon dioxide was present. These molecules had been predicted by models of what a sub-Neptune atmosphere might look like. But there was an anomaly, a peak in the spectrum that did not match any expected compound. The team ran their analysis again. They checked their instruments. They consulted with colleagues. The peak remained. It was dimethyl sulfide. The announcement, when it came, was measured, scientific, cautious. The researchers noted that the detection was preliminary, that more observations would be needed, that alternative explanations could not be ruled out entirely. But beneath the careful language, something extraordinary was happening. For the first time in human history, we had detected a molecule associated with life in the atmosphere of a potentially habitable world. The implications rippled outward. News organizations picked up the story. Social media buzzed with speculation. Some called it the greatest discovery in the history of science. Others urged patience, reminding us the preliminary results have been wrong before. The scientific community split along familiar lines. Optimists argued that the evidence was compelling. Skeptics pointed out that we still knew very little about the planet's true nature. Both sides were right. The detection of dimethyl sulfide, if confirmed, would be one of the most significant discoveries ever made. But confirmation was essential. Science does not run on excitement. It runs on verification, replication, and the slow accumulation of evidence that eventually becomes impossible to deny. So where do we stand today? The data from JWST is being analyzed and reanalyzed. Additional observations have been requested and approved. Other telescopes are being brought to bear on the problem. Within a few years, we will know whether the dimethyl sulfide signal is real or an artifact of noise and wishful thinking. But even if the signal proves to be real, questions will remain. How did the molecule get there? What is producing it? Could there be abiotic processes, chemical reactions without life that we simply have not considered? Kate 118 billion is not Earth. Its atmosphere is dominated by hydrogen. Its surface, if it has a surface, is nothing like our own. The conditions that produce dimethyl sulfide on our planet may not apply there, and yet the molecule is there. The signal is clear, and every scientist who has looked at the data has been forced to confront a possibility that once seemed confined to science fiction. There may be life on Kate 118 billion. Not intelligent life, not civilizations building telescopes of their own, but life. Organisms, cells dividing, metabolizing, releasing waste products into an alien atmosphere. If that is true, then the universe is not the empty void we once imagined. It is teeming with existence. Every star we see may harbor worlds. Every world may harbor chemistry. And some of that chemistry may have crossed the threshold into something we recognize as alive. This is the signal we have been waiting for. This is the message written in light across 120 years of empty space. This is the story we will tell our children, and they will tell theirs. The story of how we learned that we are not alone. But the story is not over. It has barely begun. Because Kate 28 billion is more than a signal. It is a world, a place with weather and seasons and landscapes we can only imagine. And if we are to understand what lives there, we must first understand what the planet itself is like. We must travel in our minds across that vast distance. We must stand on whatever surface exists beneath that hydrogen sky. We must ask what kind of world could produce the molecule of life. That journey begins in the next chapter. A world between worlds. A planet unlike anything in our solar system. A place where the boundaries between ocean and sky blur into something new. Kate 118 billion awaits. And what we find there will challenge everything we thought we knew about where life can exist. The red dwarf star hangs in the sky. Larger than our sun appears from Earth, but dimmer, casting an orange glow across a world of hydrogen and water and mystery. Somewhere below in oceans we cannot see, something may be living. Something may be breathing out the molecule that crossed the cosmos to reach us. Something may be waiting to be discovered. The signal has been received. The question has been asked. The answer is out there, 120 light-years away, floating in an atmosphere of methane and carbon dioxide and dimethyl sulfide. And for the first time in history, we have the tools to find it. This is not science fiction. This is science fact. This is happening now, and you are here to witness it. Welcome to the search for life beyond Earth. Welcome to the story of Kate 28 billion. Welcome to the moment everything changes. The universe has spoken. Now we must learn to listen. Chapter 2. A world between worlds. To understand what may be living on Kate 118 billion, we must first understand the planet itself. And to understand the planet, we must abandon almost everything we know about worlds. Because Kate 118 billion belongs to a category of planets that does not exist in our solar system. It is something new, something strange, something that challenges the very definition of what a planet can be. In our cosmic neighborhood, we have two basic types of worlds. Rocky planets like Earth, Mars, Venus, and Mercury. Small, dense, with solid surfaces you could theoretically stand on. And gas giants like Jupiter and Saturn. Massive, bloated with no surface at all, just atmosphere all the way down, thickening into liquid and eventually into a core of compressed matter under unimaginable pressure. Kate 118 billion is neither of these things. It is what astronomers call a sub-Neptune, a planet larger than Earth but smaller than Neptune, with a mass 8.6 times that of our home world and a radius about 2.5 times greater. If you stood on Earth and could somehow see Kate 118 billion beside it, our planet would look like a marble next to a softball. But size alone does not make Kate 28 billion special. What makes it special is what may lie beneath its hydrogen-rich atmosphere. Because according to the leading theories, Kate 28 billion may not be a miniature gas giant at all. It may be something far more interesting. A Hycean world. The term Hycean was coined in 2021 by Dr. Niku Madhusudhan, an astrophysicist at the University of Cambridge who has spent his career studying exoplanet atmospheres. The word combines hydrogen and ocean, and the concept is revolutionary. A Hycean world is a planet with a thick hydrogen atmosphere above a global liquid water ocean. No continents, no land, just water all the way around, covered by a sky of hydrogen that would be lethal to humans but potentially hospitable to other forms of life. The idea seems counterintuitive at first. Hydrogen is the lightest element. On Earth, any hydrogen released into the atmosphere quickly escapes into space because our gravity is not strong enough to hold it. But Kate 118 billion is much more massive than Earth. Its gravity is stronger. A hydrogen atmosphere could persist for billions of years, wrapped around the planet like a blanket. And that blanket does something remarkable. It creates a greenhouse effect, but not like the one warming our own planet. Hydrogen is transparent to visible light, but traps infrared radiation. The result is a world that can maintain liquid water temperatures even at distances from its star, where traditional models would predict frozen ice. The habitable zone, the region where liquid water can exist, expands dramatically for Hycean worlds. Planets that seem too cold for life suddenly become candidates. Kate 118 billion orbits its red dwarf star at a distance of about 14 million miles, which in our solar system would place it far inside the orbit of Mercury, practically touching the Sun. But Kate 118 is not the Sun. It is a cool, dim member of a star, radiating perhaps 1/40th the energy of our Sun. At 14 million miles, Kate 118 billion receives roughly the same amount of starlight that Earth receives. The temperatures beneath that hydrogen atmosphere could be warm enough for liquid water, warm enough, perhaps, for life. The surface temperature of Kate 28 billion has been estimated at approximately 120 degrees F. That is hot by human standards, a scorching summer day that never ends, but it is well within the range where liquid water can exist. And it is cooler than many environments on Earth where life thrives. Hydrothermal vents at the bottom of the ocean reach temperatures of 700 degrees F, and bacteria flourish there. Hot springs in Yellowstone bubble at near-boiling temperatures, and colorful mats of microbes paint their edges. Life, we have learned, is remarkably tolerant of heat, but the temperature is only part of the story. What about pressure? What about the chemistry of the atmosphere? What about radiation from the star? Each of these factors shapes what kind of life could exist, if life exists at all. The pressure at the surface of Kate 118 billion, if there is a surface, would be immense. The weight of that hydrogen atmosphere pressing down would create conditions unlike anything on Earth. Imagine the bottom of the ocean, but instead of water above you, there is gas. Dense, hot, pressing against whatever structures might exist. Any life form in that environment would need to be adapted to pressures that would crush a human body. But again, life on Earth has shown us what is possible. Creatures living in the deepest ocean trenches, miles below the surface, experience pressures of over 16,000 pounds per square inch. They have evolved bodies that function in those conditions. There is no physical law that says life cannot exist under high pressure. Only our own experience, limited to one planet, suggests otherwise. The atmosphere itself presents both challenges and opportunities. Hydrogen is not inherently toxic to life. Many microorganisms on Earth metabolize hydrogen as an energy source. The presence of methane and carbon dioxide, both detected by JWST, suggests a chemically active atmosphere. On Earth, these gases are involved in the carbon cycle, the process by which carbon moves through living organisms and the environment. Their presence on Kate 28 billion hints at processes that could support biological activity. And then there is dimethyl sulfide, the molecule that started this entire investigation. On Earth, DMS is produced when marine organisms break down a compound called dimethylsulfonopropionate, or DMSP. Phytoplankton, the microscopic plants that form the base of the ocean food chain, produce vast quantities of DMSP. When they die, or when they are eaten by zooplankton, the compound breaks down and releases DMS into the atmosphere. The presence of DMS in an alien atmosphere suggests one of two possibilities. Either there is some unknown chemical process that can produce the molecule without life, or there are organisms on Kate 118 billion, perhaps floating in whatever ocean exists beneath the hydrogen sky, that are metabolizing sulfur compounds and releasing DMS as a byproduct. The first possibility cannot be ruled out. The second changes everything. Let us imagine for a moment what Kate 28 billion might actually look like. We do not have photographs. JWST cannot image the planet directly at this distance. Everything we know comes from indirect measurements, from the light that passes through the atmosphere during transits. But science allows us to construct reasonable models, and those models paint a picture both alien and strangely familiar. The planet may have no solid surface at all. The hydrogen atmosphere could simply grow denser and denser as you descend, eventually transitioning into a supercritical fluid, a state of matter between gas and liquid. Beneath that, a layer of water. Not frozen, not boiling. Liquid water, perhaps thousands of miles deep. An ocean with no bottom visible, no seafloor, just water all the way down until pressure and temperature transform it into exotic ices, under such compression that they would be hot to the touch. If life exists in that ocean, it would be unlike anything we have ever seen. There would be no sunlight penetrating to any meaningful depth. The hydrogen atmosphere would filter out most radiation. Any photosynthesis would have to rely on wavelengths of light we barely use on Earth. Or life would have to find energy from other sources entirely. Chemosynthesis, perhaps, the same process that powers ecosystems around hydrothermal vents on our own planet. Organisms drawing energy from chemical reactions rather than sunlight. Picture creatures drifting in eternal darkness. No eyes because there is nothing to see. No plants because there is no light to grow. Just organisms metabolizing whatever chemicals their environment provides, reproducing, evolving, existing in a world we can barely imagine. Or perhaps the picture is different. Perhaps Kate 118 billion has clouds of complex organic compounds raining down nutrients into the ocean below. Perhaps there are layers in the atmosphere where temperature and pressure allow for floating ecosystems, organisms that never touch the water but drift forever in the sky. We do not know, we cannot know yet, but the possibilities are vast. The red dwarf star Kate 118 adds another layer of complexity. Red dwarfs are not like our sun. They are smaller, cooler, and far more long-lived. Our sun has been burning for about 4.5 billion years and will continue for another 5 billion before expanding into a red giant and consuming the inner planets. Red dwarfs burn for trillions of years. They are miserly with their fuel, releasing energy slowly, glowing for epochs longer than the current age of the universe. This means that Kate 118 billion has had time. Time for chemistry to become complex. Time for self-replicating molecules to emerge. Time for evolution to work its slow magic. The planet is estimated to be about 2.5 billion years old. That is younger than Earth, which formed 4 billion years ago, but it is still an enormous span of time. Life on Earth took only about 500 million years to appear after the planet formed. If the same processes occurred on Kate 118 billion, there has been more than enough time for life to emerge and evolve. But red dwarfs also present challenges. They are prone to flares, sudden bursts of radiation that can be thousands of times more intense than anything our sun produces. These flares can strip away atmospheres, bombard surfaces with harmful radiation, and make conditions hostile to life as we know it. Kate 118 billion, orbiting so close to its star, would be exposed to these flares regularly. However, the thick hydrogen atmosphere could provide protection. Hydrogen is excellent at absorbing certain types of radiation. The atmosphere could act as a shield, blocking the worst of the stellar flares and allowing conditions below to remain stable. We simply do not know enough yet to say whether the flares are a fatal problem or a manageable nuisance. There are also questions about the planet's rotation. Many planets orbiting close to red dwarfs become tidally locked, meaning one side always faces the star and the other side always faces away. Eternal day on one hemisphere, eternal night on the other. The temperature difference between the two sides could be extreme, with scorching heat on the day side and frozen darkness on the night side. If Kate 28 billion is tidally locked, life would face additional challenges. It might be confined to a narrow band around the terminator, the line between day and night where temperatures are moderate. Or it might have evolved ways to circulate between the two hemispheres, following currents in the ocean or drifting on atmospheric winds. We are speculating now, informed speculation based on physics and chemistry and what we know about life on Earth, but speculation nonetheless. The truth is that Kate 28 billion is a mystery. We have glimpsed it through the narrowest of windows. A few molecules detected in starlight that has traveled for over a century. We know almost nothing about its surface, its weather, its geology, its history. We know only that something there is producing a molecule that on Earth is produced only by life. That is enough. That is enough to justify years of observation, billions of dollars of investment, the focused attention of thousands of scientists around the world. Because if life exists on Kate 118 billion, it changes our understanding of the universe. It means that life is not a cosmic accident, a one-time fluke that happened on one lucky planet. It means that life is a process, a tendency of matter to organize itself into self-replicating patterns wherever conditions allow. And if that is true, then the universe is alive. Not just on Earth, not just on Kate 118 billion, but everywhere. On billions of planets orbiting billions of stars in billions of galaxies. Life spreading across the cosmos like fire across a forest, inevitable and unstoppable. Kate 28 billion is a world between worlds. Too large to be Earth, too small to be Neptune, too strange to fit neatly into our categories. But perhaps that is the lesson. The universe does not care about our categories. It creates what it creates, following laws of physics and chemistry that apply everywhere. And sometimes what it creates is something new, something that challenges our assumptions, something that forces us to expand our definitions of what is possible. The planet hangs in space, 120 light-years away, wrapped in hydrogen and mystery. Its star glows orange in the darkness. Its ocean, if it has an ocean, stretches beneath clouds we cannot see. And somewhere in that ocean, or floating in that atmosphere, or clinging to structures we cannot imagine, something may be alive. Something may be breathing out dimethyl sulfide. Something may be the answer to our oldest question. The next chapter will examine that molecule more closely. What is dimethyl sulfide? How does life produce it? And why does its presence in an alien atmosphere matter so much? The chemistry of life, it turns out, leaves traces, signatures that persist even across the vastness of space. And we are learning to read those signatures one photon at a time. The molecule of life awaits. And with it, perhaps the proof we have been searching for since humanity first looked up at the stars and wondered. Chapter 3. The molecule of life, dimethyl sulfide, 3 words that may rewrite the story of life in the universe. 2 carbon atoms, 6 hydrogen atoms, 1 sulfur atom. A compound so simple you could sketch its structure on a napkin. And yet its presence in the atmosphere of Kate 28 billion has sent shock waves through the scientific community. To understand why this molecule matters, we need to understand where it comes from. On Earth, dimethyl sulfide has one primary source: living organisms. It is what scientists call a biosignature, a chemical fingerprint that points unmistakably toward biological activity. And unlike many other potential biosignatures, dimethyl sulfide is remarkably difficult to produce without life. The story of DMS on Earth begins in the ocean. Floating near the surface, invisible to the naked eye, are trillions upon trillions of phytoplankton. These microscopic organisms are the foundation of marine food webs. They photosynthesize like plants, converting sunlight and carbon dioxide into organic matter. They produce roughly half of all the oxygen in Earth's atmosphere, and they manufacture a compound called dimethyl sulfoniopropionic, DMSP. DMSP serves multiple purposes for the organisms that produce it. It acts as an osmotic regulator, helping cells maintain proper water balance in salty ocean water. It may protect against oxidative stress. It serves as a chemical defense against predators. Some evidence suggests it helps organisms survive temperature extremes. Whatever its primary function, phytoplankton produce it in staggering quantities. The global ocean contains approximately 1 billion tons of DMSP at any given moment. When phytoplankton die, or when they are consumed by zooplankton or bacteria, DMSP breaks down. One of the breakdown products is dimethyl sulfide. The molecule is volatile, meaning it evaporates easily. Released from the ocean's surface, it drifts upward into the atmosphere. There it participates in a complex chain of chemical reactions. It oxidizes to form sulfate aerosols. These aerosols become nucleation points for cloud droplets. Without dimethyl sulfide from marine life, Earth's clouds would form differently. Our climate would be altered. The connection between ocean life and climate through DMS is called the Claw hypothesis, named for the 4 scientists who proposed it in 1987. Charlson, Lovelock, Andre, and Warren suggested that phytoplankton regulate their own environment by producing DMS, which increases cloud cover, which reflects sunlight back to space, which cools the ocean, which affects phytoplankton populations. A feedback loop connecting microscopic organisms to planetary climate. The hypothesis remains debated, but the basic chemistry is well established. The critical point for our story is this. On Earth, there is no significant abiotic source of dimethyl sulfide. Abiotic means not involving living organisms. Volcanoes do not emit DMS. Lightning does not produce it. Chemical reactions in the atmosphere do not generate it in meaningful quantities. Wherever we find dimethyl sulfide on our planet, we find life. This is what makes the detection on Kate 118 billion so significant. If dimethyl sulfide exists in that alien atmosphere, something must be producing it. Either there is a chemical process we do not understand, one that can generate DMS without biological involvement, or there is life on Kate 28 billion, life that, like phytoplankton on Earth, metabolizes sulfur compounds and releases DMS as a byproduct. The scientific community is cautious, and they should be. We have been fooled before. In 1996, a team of NASA scientists announced they had found evidence of ancient microbial life in a meteorite from Mars. The meteorite, called ALH 84001, contained structures that looked like fossilized bacteria. The announcement made headlines around the world, and then over the following years, alternative explanations emerged. The structures could have formed through non-biological processes. The organic compounds could have been contamination from Earth. The evidence, once so compelling, became controversial and then largely rejected. The lesson was clear. Extraordinary claims require extraordinary evidence. The detection of a potential biosignature in an alien atmosphere is an extraordinary claim. The evidence must be examined from every angle before conclusions can be drawn. So let us examine the alternatives. How might dimethyl sulfide appear in the atmosphere of Kate 118 billion without life being involved? One possibility is photochemistry. Ultraviolet radiation from the star could drive chemical reactions in the atmosphere, breaking apart larger molecules and allowing them to recombine in new ways. Perhaps some combination of hydrogen, carbon, and sulfur compounds reacting under the influence of stellar radiation could produce DMS. We know that complex organic molecules can form in space through photochemistry. The question is whether this particular molecule could form in the particular conditions of Kate 118 billion's atmosphere. The model suggests it is unlikely. The chemical pathways that lead to DMS on Earth all involve biological enzymes, proteins that catalyze specific reactions at rates that non-biological processes cannot match. Without those enzymes, the reactions that produce DMS would be prohibitively slow. You might get a few molecules here and there, but not the quantities needed to produce a detectable atmospheric signature. Another possibility is geological activity. On Earth, volcanoes release sulfur compounds into the atmosphere. Could volcanic activity on Kate 28 billion produce dimethyl sulfide? The problem is that Kate 118 billion may not have any solid surface at all. If it is truly a Hycean world with a hydrogen atmosphere over a deep water ocean, there may be no volcanism in the traditional sense. And even if there were, volcanoes on Earth do not produce significant amounts of DMS. They release hydrogen sulfide, sulfur dioxide, and other sulfur compounds, but not dimethyl sulfide. A third possibility is that we are misinterpreting the data. Spectroscopy, the technique used to identify molecules in distant atmospheres, works by analyzing absorption patterns in light. Each molecule absorbs light at specific wavelengths, leaving a characteristic fingerprint, but those fingerprints can overlap. The signal attributed to dimethyl sulfide might actually be caused by some other molecule or by a combination of molecules that together mimic the DMS signature. This is why the scientific community is being careful. The detection is preliminary. More observations are needed. The statistical confidence of 99.7% sounds impressive, but in science that still leaves room for doubt. A 99.7% confidence level means that there is roughly a 1 in 300 chance the signal is a false positive. Those odds are not negligible. More data from JWST and from other telescopes will either strengthen the case or reveal that the signal was an artifact. But let us assume for the moment that the detection is real, that dimethyl sulfide truly exists in the atmosphere of Kate 118 billion. What would that mean? It would mean that somewhere on that planet, probably in the liquid water ocean that may exist beneath the hydrogen atmosphere, organisms are living and metabolizing. They are taking in nutrients, processing them chemically, and releasing waste products into their environment. One of those waste products is dimethyl sulfide. It rises through the water column, escapes into the atmosphere, and drifts among the methane and carbon dioxide and hydrogen that surround the planet. These organisms would not be like anything we know. They would have evolved in conditions utterly unlike Earth. Higher pressure, different chemistry, perhaps no sunlight at all reaching their environment. They might be single-celled like bacteria, Or they might be something more complex, multicellular life forms that have developed in isolation for billions of years. We cannot know without more information, but we can speculate about their biochemistry. On Earth, the organisms that produce DMSB and release DMS are photosynthetic creatures that derive energy from sunlight. But on Kate 118 billion, with its thick hydrogen atmosphere and potentially deep ocean, sunlight may not penetrate to where life exists. These organisms would need a different energy source. Chemosynthesis is one possibility. On Earth, ecosystems around hydrothermal vents rely on chemosynthesis, deriving energy from chemical reactions rather than sunlight. Bacteria oxidize hydrogen sulfide and other compounds released by the vents, using the energy to fix carbon and build organic molecules. These bacteria form the base of food chains that include tube worms, crabs, and fish, all living in complete darkness miles below the ocean's surface. If Kate 118 billion has similar processes, life there could be chemosynthetic. Organisms might metabolize hydrogen, which is abundant in the atmosphere, or they might use reactions involving sulfur compounds, explaining the production of dimethyl sulfide. The chemistry would be different from Earth life, but the principle would be the same. Energy flows, molecules transform, and life persists. There is another intriguing possibility. On Kate 118 billion, with its hydrogen-rich atmosphere, the basic chemistry of life might be fundamentally different from what we know. On Earth, life is based on carbon. Organic molecules, from simple sugars to complex proteins, all contain carbon atoms bonded to hydrogen, oxygen, nitrogen, and other elements. But there is no law of physics that says life must be carbon-based. Silicon, for example, can form complex molecules under certain conditions. And in a hydrogen-rich environment, entirely new kinds of chemistry might be possible. We should not get too far ahead of ourselves. The simplest explanation is usually correct. If life exists on Kate 118 billion, it is probably based on carbon, like life on Earth. Carbon is abundant in the universe, forms bonds easily, and creates the complex molecules needed for biological processes. But the possibility of truly alien biochemistry, life based on chemistry we have never imagined, cannot be ruled out entirely. The detection of dimethyl sulfide is not proof of life. Not yet. It is evidence. Strong evidence, evidence that demands investigation, and that investigation is already underway. JWST has been allocated more observation time for Kate 28 billion. The telescope will gather additional data, refining the spectroscopic measurements, and looking for other potential biosignatures. Scientists will analyze the new data and compare it to models of what abiotic chemistry could produce. The statistical confidence will either increase or decrease. Other telescopes are also being brought to bear. Ground-based observatories with high-resolution spectrographs can provide complementary data. Different instruments have different strengths and weaknesses. If multiple telescopes using multiple techniques all detect the same signal, the case for DMS on Kate 118 billion becomes much stronger. And in the background, theorists are working to understand what the detection means. If life does exist on Kate 118 billion, what can we infer about its nature? How abundant would organisms need to be to produce the detected levels of DMS? What other biosignatures might accompany the sulfur signal? Could we detect them with current technology? The molecule of life has been found, or at least the molecule that on Earth is the molecule of life. Whether it signifies biology on Kate 118 billion remains to be determined. But the search has entered a new phase. We are no longer just looking for potentially habitable worlds. We are examining specific planets for specific chemical signs of life. We are moving from possibility to evidence. That transition is the result of decades of work. The detection of dimethyl sulfide did not happen by accident. It required a machine of unprecedented capability, a telescope that can see what no telescope has seen before. The James Webb Space Telescope is the instrument that made this discovery possible. And to understand how we reached this moment, we need to understand the machine. The next chapter will take us to the telescope itself. How was it built? How does it work? How can a cluster of mirrors and sensors floating in space detect a molecule in an atmosphere 120 light-years away? The engineering is extraordinary. The science is transformative. And the story of how humans built an eye that can see across the cosmos is almost as remarkable as what that eye has found. The machine that sees through time awaits, and with it the explanation of how humanity reached across the universe and found evidence that we may not be alone. We built something wonderful, and it is showing us wonders we barely dared to imagine. Chapter 4. The Machine That Sees Through Time. On Christmas morning 2021, a rocket lifted off from a launch pad in French Guiana. In its payload bay sat a machine that had taken nearly 3 decades to design, build, and test. A machine that had consumed over $10 billion. A machine that some said would never work, could never work, was too complex, too ambitious, too delicate to survive the journey to its destination. The James Webb Space Telescope rose on a column of flame and disappeared into the sky. What happened next was either the greatest engineering achievement in the history of space exploration or the most expensive failure ever attempted. For 2 weeks, the world watched as the telescope unfolded itself in the void. 344 single-point failures, 344 things that could go wrong, each one potentially fatal to the mission. Every hinge had to swing into position. Every latch had to catch. Every motor had to function in the cold vacuum of space, far from any hope of repair. Every single component worked perfectly. The James Webb Space Telescope is the successor to Hubble, but it is not simply a larger Hubble. It is a fundamentally different kind of instrument, designed for a fundamentally different kind of science. Where Hubble sees primarily visible and ultraviolet light, JWST sees in infrared. That difference sounds technical, but it is the key to everything the telescope can do, including detecting potential signs of life on distant worlds. Infrared light is heat radiation. Everything warm emits it. Your body, a cup of coffee, the engine of a car, a distant star. But infrared light is easily absorbed by water vapor in Earth's atmosphere. A ground-based infrared telescope is essentially blind, staring up through a sky that blocks most of the light it wants to see. To see the universe in infrared, you need to get above the atmosphere and you need to be cold. That last requirement is critical. If your telescope is warm, it emits its own infrared radiation. It is like trying to photograph stars while standing next to a bonfire. The glare overwhelms everything else. To see faint infrared sources, the telescope must be colder than the things it is observing, much colder. JWST operates at a temperature of approximately -370 degrees F. That is colder than anything in our solar system, except perhaps the permanently shadowed craters at the lunar poles. The telescope achieves this by traveling to a special point in space called Lagrange 2, or LTWO, about 1 million miles from Earth in the direction away from the Sun. At LTWO, the gravitational pulls of the Sun and Earth combine to create a stable point where a spacecraft can orbit with minimal fuel. More importantly, at LTWO, the Sun, Earth, and Moon are all on the same side of the telescope. JWST deployed a sunshield the size of a tennis court to block their light and heat. Behind that shield, in permanent shadow, the telescope cooled to operating temperature. The primary mirror is the most recognizable feature of JWST. 18 hexagonal segments, each coated with a thin layer of gold, arranged in a honeycomb pattern to form a single reflecting surface 6.5 meters across. That is nearly 3 times the diameter of Hubble's mirror. And because a telescope's light-gathering power scales with the area of its mirror, not the diameter, JWST can collect roughly 6 times as much light as Hubble. It can see fainter objects, more distant objects, objects that Hubble could never have detected. The gold coating is not decorative. Gold is an excellent reflector of infrared light. The nanometer-thin layer of gold on each mirror segment bounces incoming infrared photons toward the secondary mirror, which redirects them into the telescope's instruments. There are 4 main instruments aboard JWST. NIRCam, the near-infrared camera, NIRSpec, the near-infrared spectrograph, MIRI, the mid-infrared instrument, and FGS/NIRISS, the fine guidance sensor and near-infrared imager and slitless spectrograph. Together, these instruments can image the infrared sky, break light into its component wavelengths, and analyze the chemistry of distant objects. It is NIRSpec that made the Kate Woe 118 billion discovery possible. The spectrograph takes light from a target and spreads it out like a rainbow, but an infrared rainbow invisible to human eyes. Each wavelength corresponds to a specific amount of energy. When light passes through a gas, certain wavelengths are absorbed by molecules in that gas. The absorbed wavelengths appear as dark lines or dips in the spectrum. By identifying which wavelengths are missing, scientists can determine which molecules are present. This technique, called transmission spectroscopy, is how we study exoplanet atmospheres. We wait for a planet to pass in front of its star. As it transits, a tiny fraction of the starlight passes through the planet's atmosphere before continuing onto us. That light carries the fingerprints of whatever molecules it encountered. Methane absorbs at certain wavelengths, carbon dioxide at others, water vapor, ammonia, hydrogen, sulfide. Each has its own distinctive signature, and dimethyl sulfide. It too has a fingerprint, a pattern of absorption that says this light has passed through a gas containing 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom arranged in this particular way. When scientists analyzed the JWST spectrum of K28 billion, they found that fingerprint. The detection was not easy. The signal was faint. K28 billion is 120 light-years away. Even with JWST's enormous mirror, the amount of light reaching the telescope is minuscule. The planet itself does not emit much light. We are seeing it only by the starlight that filters through its atmosphere, a tiny sliver of photons from an already dim star. Teasing out the molecular signatures required hours of observation time and sophisticated data analysis. Computer algorithms compared the observed spectrum to models of what different atmospheric compositions would produce. The best fit included dimethyl sulfide, but the telescope's capabilities extend beyond atmospheric chemistry. JWST has already transformed our understanding of the universe in multiple ways. It has imaged galaxies that formed within a few 100 million years of the Big Bang, revealing that the early universe was more structured and complex than theories predicted. It has observed the atmospheres of planets in our own solar system in unprecedented detail, finding new features on Jupiter and Saturn. It has peered into stellar nurseries, the clouds of gas and dust where new stars are born, and revealed the intricate processes of star formation. One capability is particularly relevant to the search for life. JWST carries a coronagraph, a device that blocks out the light of a star so that objects orbiting near it become visible. Stars are blindingly bright compared to their planets. A star like our Sun outshines an Earth-like planet by a factor of about 10 billion. Without some way to block the starlight, the planet would be invisible, lost in the glare. Coronagraphs work by placing a small opaque disk in the light path, positioned precisely to cover the star while allowing light from nearby objects to pass. The technique is delicate. The star's light can scatter and diffract around the disk, creating artifacts that obscure faint companions. JWST's coronagraph is the most sophisticated ever flown, capable of suppressing starlight by factors of thousands to tens of thousands. It has already been used to directly image exoplanets, including planets in the Beta Pictoris system. The combination of infrared sensitivity, massive light-gathering power, and coronagraphic capability makes JWST uniquely suited to study other worlds. It can analyze atmospheres through transmission spectroscopy. It can image planets directly under favorable conditions. It can detect heat emissions from hot, young worlds. It is, in short, the perfect tool for the moment we find ourselves in. The moment when detecting signs of life on other planets has become technically possible. But JWST did not appear from nowhere. Its existence is the result of decades of effort, persistence in the face of setbacks, and the determination of thousands of scientists and engineers who believed that such a telescope should exist. The story of its creation is a story of ambition pushed to the edge of feasibility. The concept for a next-generation space telescope began taking shape in the late 1980s. Hubble had not yet launched, but planners were already thinking ahead. What would come after Hubble? What capabilities would the scientific community need in the decades ahead? A committee convened in 1989 recommended a large infrared telescope in space. The idea would evolve over the next decade into the James Webb Space Telescope. The initial budget was $200 million. The final cost exceeded $10 billion. That escalation caused political controversy and nearly killed the project multiple times. In 2011, the House Appropriations Committee voted to cancel JWST entirely, calling it billions of dollars over budget and plagued by poor management. The scientific community rallied in defense. Letters were written, meetings were held. Eventually, the Senate restored funding and the project continued. The delays were partly due to technical challenges. Building a mirror that could unfold in space had never been done. Building a sunshield of that size and complexity had never been done. The instruments pushed the limits of what was possible. Every component had to function flawlessly in an environment that no human could reach to fix. The testing was exhaustive, and when problems were found, they had to be corrected before launch. Some critics argued the money should have been spent elsewhere. $10 billion could fund many smaller missions. But JWST's proponents insisted that some science can only be done with large telescopes. You cannot build 10 small telescopes and combine their results to equal one large telescope. The physics does not work that way. Certain observations require a certain scale of instrument, and the observations JWST enables, including the potential detection of biosignatures on distant worlds, justify the investment. Now the telescope is in space, functioning beautifully, exceeding expectations. Its data is transforming astronomy. Papers are being published at a furious rate. Discoveries are announced monthly. And among those discoveries is the detection of dimethyl sulfide on Kate 118 billion, a detection that might not have been possible with any other instrument. The machine that sees through time has delivered. But what has it delivered exactly? What does it mean to find a molecule associated with life in an alien atmosphere? That is the question we must grapple with. The data is in. The analysis has been done. The statistical confidence is high. But interpretation requires understanding not just what was found, but what could explain it. And to do that, we need to imagine what life in a hydrogen ocean might look like. We need to consider possibilities that go beyond anything Earth has shown us. The next chapter will dive into that hydrogen ocean. What kind of creatures could live there? How would they survive? What would they eat? And how would they reproduce? If dimethyl sulfide is being produced on Kate 28 billion, something must be producing it. And that something, if it exists, would be one of the strangest forms of life we have ever contemplated. Welcome to the ocean beneath the hydrogen sky. Welcome to life in a place where everything we know might not apply. Welcome to the realm of pure possibility. JWST has shown us the door. Now we must imagine what lies beyond it. What lives in hydrogen oceans? That is the question. And the answer, if there is an answer, will change everything we think we know about the nature of existence itself. Chapter 5. What lives in hydrogen oceans? Close your eyes for a moment and imagine you are floating in water, but not water as you know it. The pressure is immense, perhaps hundreds or thousands of times what you would feel at the bottom of Earth's deepest ocean. There is no light, none. The darkness is absolute. Above you, somewhere impossibly far, is an atmosphere of hydrogen and methane, thick as soup, pressing down with the weight of an entire world. Below you, the water continues, miles and miles of it, eventually transforming into exotic ices under pressure so great that the molecular structure of water itself changes. This is the hydrogen ocean of Kate 118 billion, or at least this is what the model suggests. A world wrapped in hydrogen, with liquid water beneath and darkness everywhere. If life exists here, it exists in conditions that would kill every complex organism on Earth. And yet something may be breathing out dimethyl sulfide into that alien atmosphere. Something may be alive down there in the dark. What could that something be? On Earth, life requires certain things, energy either from sunlight or from chemical reactions, liquid water as a solvent for biochemistry, carbon as the backbone of organic molecules, and time for evolution to work its patient magic. Kate 118 billion may have all of these things. The question is whether it has them in the right combinations and whether the conditions allow the complex chemistry of life to emerge and persist. Let us start with energy. On Earth, most ecosystems are powered by sunlight. Plants and photosynthetic bacteria capture light energy and convert it into chemical energy, which then flows through food webs as organisms eat each other. But sunlight is not the only energy source life can use. In the deep ocean, far from any ray of sun, entire ecosystems thrive on chemosynthesis. Hydrothermal vents are cracks in the seafloor where superheated water, rich in chemicals from the Earth's interior, gushes into the cold deep. The temperature gradient and the chemical compounds in that water provide energy that microorganisms can harvest. These microorganisms, mostly bacteria and archaea, form the base of a food chain that includes tubeworms, clams, shrimp, crabs, and fish. None of these creatures ever see sunlight. They do not need it. They live entirely on energy derived from the chemistry of the planet itself. Kate 118 billion, if it has a rocky core beneath its ocean, might have similar processes. Water circulating near that core could pick up chemicals and release them into the ocean above. Organisms adapted to those conditions could harvest the energy. And as those organisms metabolized, they might produce dimethyl sulfide as a byproduct, just as marine life on Earth does. But there is another possibility, one that requires us to think even more creatively. In a hydrogen-rich atmosphere, hydrogen itself becomes a potential energy source. On Earth, there are microorganisms called hydrogen-oxidizing bacteria that consume hydrogen gas and use it to drive their metabolism. They combine hydrogen with oxygen or other electron acceptors, releasing energy in the process. These organisms are found in environments where hydrogen is available, including around hydrothermal vents and in certain soils. On Kate 118 billion, hydrogen would be abundant. The entire atmosphere is dominated by it. If organisms evolved to metabolize hydrogen directly, they would have an almost unlimited energy supply. They would not need light or chemical vents. They could potentially survive anywhere in the ocean where temperature and pressure allowed. The metabolism of these hypothetical organisms would be unlike anything on Earth. We can speculate about the chemistry, but we cannot know for certain what reactions would be involved. Perhaps they would combine hydrogen with carbon compounds, building organic molecules while releasing energy. Perhaps they would use sulfur compounds, explaining the production of dimethyl sulfide. The details would depend on what chemicals were available and what enzymes evolved to catalyze the necessary reactions. Speaking of enzymes, this brings us to another fundamental question. What would the biochemistry of Kate 118 billion life be based on? On Earth, all known life uses DNA or RNA to store genetic information, proteins built from amino acids to carry out functions, and a variety of other organic molecules for structure and energy storage. Would life on another world use the same building blocks? The conservative answer is probably yes. Carbon is the best element for building complex molecules. It forms 4 bonds, can create long chains and rings, and participates in a vast variety of chemical reactions. The molecules of Earth life, amino acids and nucleotides and sugars, are all based on carbon. And carbon is abundant throughout the universe. It is produced in stars and distributed by supernovae. Any world with the chemistry to support life would almost certainly have carbon available, but the specific molecules might be different. The genetic code on Earth uses 4 nucleotide bases. There is no fundamental reason it could not use 6 or 8, or some entirely different set. The amino acids in Earth proteins number about 20. Other amino acids exist and could potentially serve the same functions. Life on Kate 28 billion might use familiar chemistry and unfamiliar combinations, or it might have stumbled onto entirely different solutions to the same problems. The physical form of these organisms is even harder to imagine. On Earth, life ranges from bacteria smaller than a micrometer to blue whales over 20 meters long. The constraints that determine size are gravity, available resources, and the physics of structural materials. On Kate 28 billion, with its higher gravity and different resources, those constraints would be different. Single-celled organisms are the most likely. Complex multicellular life requires stable conditions for long periods, sufficient energy to maintain complex bodies, and evolutionary time to develop from simpler forms. While Kate 118 billion might have had time for such evolution, the harsh conditions suggest that simpler life forms would be more likely. Microorganisms floating in the ocean, perhaps forming mats or colonies, metabolizing whatever chemicals their environment provides. But we should not rule out greater complexity too quickly. On Earth, multicellular life arose independently at least dozens of times. Once the basic machinery of cells exists, the evolution of cooperation between cells seems to follow naturally. If Kate 118 billion has had life for billions of years, that life might have achieved levels of complexity we do not expect. The absence of light creates a particular challenge for any life form. On Earth, even in the deep ocean, organisms have evolved to navigate, find food, and locate mates. They do this through a variety of senses. Some use bioluminescence, producing their own light to communicate or lure prey. Others sense chemical gradients, following traces of food through the water. Some detect the magnetic field of the Earth. Some use pressure waves, a form of touch at a distance. Life on Kate 28 billion would need similar adaptations. Perhaps organisms there produce light, brief flashes in the darkness to signal each other. Perhaps they navigate by taste, following chemical trails through the water. Perhaps they have senses we cannot imagine, detecting aspects of their environment that have no analog on Earth. There is something haunting about imagining these creatures, beings that have never seen a ray of sunlight, that do not know the concept of day and night, that exist in a world of pressure and chemistry and eternal darkness. If they are intelligent, which is unlikely but not impossible, what would they think about? What would be their equivalent of astronomy, their way of wondering about the universe beyond their dark ocean? We are getting ahead of ourselves. Intelligence requires brain structures that took billions of years to evolve on Earth. Simple microorganisms are far more likely on Kate 118 billion. But even simple microorganisms are miraculous. A single cell reproducing itself, passing information to the next generation, adapting to its environment over countless generations. If that exists on Kate 28 billion, it changes everything. The detection of dimethyl sulfide suggests that something is producing sulfur compounds. On Earth, the organisms that do this are often bacteria or archaea, ancient lineages that diverged from the common ancestor of all life billions of years ago. These microorganisms are incredibly diverse, filling every niche where chemistry allows. Some live in acid hot springs, some survive in Antarctic ice, some dwell in rocks miles below the surface. They are the most resilient and adaptable organisms we know. If life Kate 118 billion is a lot like Earth bacteria in how it can use many kinds of food and energy, so the hard conditions on that planet might not stop life. Life finds a way, it adapts, it evolves, it fills whatever spaces are open to it. The hydrogen ocean of Kate 28 billion, even if it feels unfriendly to us, might be a perfect home for living things that fit that world. We must also think about the chance that life on Kate 118 billion is not like Earth life at all. Not just different in small ways, but different in big ideas. What if it uses silicon instead of carbon? What if it stores information in ways we have never even imagined? These ideas seem unlikely, but we cannot ignore them. We have only one example of life to study. Our ideas about what life needs are built on that one example. They might be rules that work everywhere, or they might be local assumptions that will be proven wrong when we meet something truly alien. The dimethyl sulfide detection does point to chemistry we know from Earth. If that molecule is being made by life on Kate 118 billion, then the biochemistry probably looks like what we already understand. Sulfur compounds being changed by enzymes, carbon atoms being moved between molecules, energy being caught, stored, and used. This is comforting in a way. It suggests that if we do find life there, we might have a chance to understand it. But even understanding has problems. How do you study an ocean that is 120 light-years away, hidden under an atmosphere of hydrogen? You cannot send a submarine. You cannot gather samples. You can only watch from far away, collecting photons that have traveled for more than a century and guessing what you can from the faint clues they bring. For now, our tools are mostly spectroscopy. We study the light passing through the atmosphere and read the molecules it has touched. But as technology improves, new chances may appear. Future telescopes might take clearer pictures of exoplanets in much more detail. Future probes might travel to nearby stars, though Kate 118 billion is far too far for any probe we could build anytime soon. Future advances in physics might show new ways to gather information across huge distances. These are dreams for another century. Today we have JWST, we have spectroscopy, we have a detection of dimethyl sulfide that might be the first evidence of life beyond Earth. And we have our imagination, guided by science but still free to wonder. Something might be living in that hydrogen ocean. Something might be moving through endless darkness, using strange chemicals for energy, reproducing in ways we do not understand. Something might be the answer to our oldest question. If it is there, we will find it. Maybe not today. Maybe not this decade, but someday, with patience and technology and the persistence that has defined our species since we first looked up at the stars, we will know. The next chapter will turn to another discovery, another world, another look at what the universe holds. The young star Beta Pictorius and the planets forming in its debris disk. JWST has seen them too, and what it has found there adds another piece to the puzzle of how planets form, how systems change, and how life might begin across the cosmos. The hydrogen ocean waits, and so do we. waiting for more data, more observations, more certainty, waiting for the answer that will change everything. Something is out there. The evidence points that way, and the search continues. Chapter 6. The Young Star and Its Children. 63 light-years from Earth in the southern constellation Picta. A star is doing something amazing. It is building planets. Not in the distant past, not billions of years ago when our own solar system formed, but right now, at least in cosmic terms, the star is called Beta Pictor, and it is one of the most studied objects in the sky. Because when we look at Beta Pictorius, we see our own past reflected back at us. We see what the sun looked like when it was young. We see the raw material of worlds being shaped by gravity and time. Beta Taurus is about 23 million years old. That sounds old by human standards, but for stars, it is a baby. Our sun is 41/2 billion years old, almost 200 times older than Beta Taurus. When Beta Pictorus was born, dinosaurs had been gone for over 60 million years. But mammals were still small animals running through the brush. The star is so young that light from its birth has not yet reached the far side of our galaxy. What makes Beta Pictorus special is not only its youth, but what is around it. In 1984, astronomers using a ground-based telescope found something incredible. A disk of material circling the star, seen edge-on from our view, stretching hundreds of astronomical units in both directions. This was the first debris disk ever directly imaged around another star. It proved that the processes we thought made our solar system were happening elsewhere, right now, around other suns. The debris disk of Beta Pictorus is not a smooth, plain ring. It has structure, warps and gaps and uneven parts that tell a story of gravity at work. Something is shaping the disk. Something is clearing paths through the debris. That something, scientists suspected, was planets. The first planet was confirmed in 2008. Beta Pictorius b is a gas giant about 11 times the mass of Jupiter, orbiting about 9 astronomical units from its star. That is about the same distance as Saturn is from our sun. The planet was found through direct imaging, one of the first exoplanets ever photographed. In pictures, it looks like a tiny dot of light beside the bright glare of its star, separated by careful image processing that removes starlight and shows what is orbiting nearby. But Beta Pix b was not alone. The shape of the debris disk hinted at more planets. Gaps in the disk appeared at distances where no known planet orbited. The disk's warp showed the pull of gravity from something unseen. Scientists searched for years using many methods, until at last a second planet showed up in the data. Beta Piscitor c was confirmed in 2019 using a method called radial velocity. As a planet orbits its star, it tugs the star slightly toward us and away from us. This movement causes tiny shifts in the star's light. Blue shifts as it comes closer and red shifts as it moves farther. By measuring these shifts with extreme care, astronomers can find planets they cannot see directly. Beta Pictorius c orbits closer to its star than Beta Pictorius b, at about 2.7 astronomical units. It is smaller than its partner, about 8 times the mass of Jupiter. Together, the two planets explain much of the disk's structure. Their gravity clears gaps, stirs material, and shapes the ring of dust and rock around their young star. But the James Webb Space Telescope has added new depth to what we know. With its infrared vision and coronagraph ability, JWST can see the Beta Picture system like no telescope before. And what it has found there shines light not only on one star system, but on the way all planetary systems, including ours, are born. The coronagraph is the key technology here. Stars are bright, planets are dim. The brightness difference between Beta Pictorius and its planets is huge, maybe 100,000 to 1 or even more. Without a way to block starlight, the planets would be invisible, lost in the glare like fireflies next to a searchlight. JWST's coronagraph puts a small dark mask in the light path, placed exactly to cover the star. Light from the star is blocked. Light from nearby objects, slightly offset from the covered area, can still reach the detectors. The method is delicate. Starlight scatters and bends around the mask, making patterns that must be carefully separated from real signals. But when it works beautifully. Planets appear from the darkness, glowing in infrared, their heat making them visible against the cold background of space. The observations of Beta Puris have revealed details impossible to see before. The debris disk shows fine structure, lanes and clumps, and density changes that show the history of crashes and gravitational pushes. The planets themselves have been measured more precisely, their temperatures checked, their orbits improved, and hints of more structure, maybe even more planets, have shown up in the data. One of the most interesting results involves the gaps in the disk. The known planets explain some of them, but not all. There are places where debris has been cleared, but where no planet has been found. Either those gaps were made by planets that later moved elsewhere, or there are planets still hiding in the system, too small or too cool for our current tools to detect. The search continues. JWST will observe Beta Taurus again, collecting more data and sharpening the picture. Ground-based telescopes with advanced adaptive optics are also watching. Within a few years, we may learn whether the system has 3 planets or 4 or more. We may learn exactly how the debris disk is being shaped and what the final layout of the system will be. Why does this matter for the search for life? Because Beta Pictorius shows us planet formation in action. The processes happening there are the same processes that made Earth. The debris disk holds the raw materials of worlds, dust and rock and ice, that will eventually join into planets or be blown away by stellar wind. The planets already formed are shaping their surroundings, creating zones where other planets might form, or where asteroids and comets might bring water and organic compounds to rocky worlds. Understanding these processes helps us guess where life-friendly planets might exist. Not every star system is equally welcoming. Some have debris disks that are too thin, without enough material to build rocky planets. Some have giant planets in orbits that would mess up the paths of smaller worlds. Some have conditions that would stop liquid water from existing anywhere in the system. Beta Taurus, even though it is young, already shows signs of the kinds of structure that can make a system possibly habitable. The giant planets orbit at a good distance, similar to where Jupiter and Saturn orbit in our system. This matters because giant planets can be both dangers and protectors. They can throw asteroids and comets inward, hitting rocky planets with impacts. But they can also clear debris from the inner system, lowering the impact rate over time. The location of giant planets affects whether life on smaller worlds has enough time to evolve before being wiped out by cosmic crashes. The debris disk itself is a storage place for water ice and organic compounds. Comets forming in the outer parts of the disk could someday deliver these materials to any rocky planets that form closer to the star. On Earth, much of our water may have arrived this way, carried by comets and asteroids during the heavy bombardment period early in our solar system's history. The oceans we swim in, the water we drink, may have started in a debris disk much like the one around Beta Pictor. JWST can study what the debris disk is made of using spectroscopy. By examining the infrared light scattered and released by dust grains, scientists can tell what minerals and ices are present. Silicate, the stuff of rocks; water ice, the source of oceans; carbon compounds, the building blocks of life. The disk around Beta Taurus contains all of these. The ingredients for life are there, waiting to be put together. There is a deep connection between what we see at Beta Puris and what we are studying at Kate 118 billion. Beta Urus shows us how planetary systems form, how the raw materials of life spread out, and how the structure of a system is set. Kate 28 billion shows us what might happen after billions of years, when a planet has had time to cool, build an atmosphere, and maybe host life. They are 2 chapters in the same story, separated by billions of years but linked by the same physical rules. The universe is consistent. The laws of physics are the same everywhere. Gravity pulls matter together here and 120 light-years away, and 63 light-years away, and in galaxies billions of light-years distant. Chemistry follows the same rules. Carbon bonds with hydrogen and oxygen and nitrogen in the same ways, making the same kinds of molecules. When we study Beta Puris, we learn about Kate 118 billion. When we study Kate 118 billion, we learn about our own past. This is the power of astronomy. Each observation adds to a picture that spans the whole cosmos. Every star tells part of the story. Every planet shows another possibility. And slowly, piece by piece, the picture becomes clearer. The picture of how matter builds itself into stars and planets and moons. The picture of how chemistry becomes biology. The picture of how the universe, through the unthinking work of physical laws, creates observers who can look back and wonder. Beta Pictorius will keep changing. Over the next 100 million years, the debris disk will thin as material is gathered into planets or blown away by stellar radiation. The planets will settle into their final orbits. If rocky worlds form in the inner system, they will cool and build atmospheres. Maybe in a few billion years, one of those worlds will host life. Maybe intelligent beings will look back at their young son and try to understand how their world began. We will not be there to see it, but we can see the beginning. We can watch the process happen. And by doing that, we connect ourselves to a cosmic story far bigger than any human lifetime. The young star and its children teach us patience, teach us scale, teach us that the universe runs on timelines we can barely understand. But they also teach us hope. Because if planet formation is happening at Beta Pictorius, it is happening around countless other stars. The galaxy is full of young systems, full of debris disks, full of worlds being made. And some of those worlds, given time, may host life. The evidence is growing from Kate Wo 118 billion, a molecule that hints at biology. From Beta Pictorius, a system that shows how planets form. From JWST, the ability to see both with amazing clarity. The pieces are coming together. The next chapter will look at how we see these distant worlds. The technology of blocking starlight, of pulling faint signals out of overwhelming noise, shadow, and light. The methods that make the impossible possible. The engineering that turns curiosity into knowledge. JWST is a machine of shadow and light, and what it reveals in those shadows may be the answer to our oldest question. The young star burns, its children orbit, and we watch from across the light years, learning what we can, dreaming of what we might find next. Chapter 7. Shadows and Light. To see a planet orbiting another star is to do a magic trick using physics. The star is there, blazing with the fire of nuclear fusion, pouring out energy in amounts that are hard to imagine. A typical star like our Sun changes 4 million tons of matter into energy every second. It has been doing this for 4 billion years, and will keep doing it for another 5 billion. The light it makes is so strong that from Earth, 93 million miles away, you cannot stare at it without hurting your eyes. Now imagine a planet orbiting that star, a rocky world like Earth or a gas giant like Jupiter. This planet does not make its own light. It reflects a tiny bit of the starlight that hits it and gives off a faint infrared glow from its own heat. Compared to the star, the planet is almost invisible. The brightness difference between a star and an Earth-like planet in its habitable zone is about 10 billion to 1. Trying to see that planet is like trying to see a firefly next to a lighthouse from 1,000 miles away. And yet we do it. We have created methods that let us find planets, study their atmospheres, and look for signs of life. These methods depend on one basic idea. Light carries information. If we can separate the light from a planet from the overwhelming glare of its star, we can learn what that planet is made of, what gases fill its atmosphere, and maybe whether anything is alive there. The oldest method is the transit method. When a planet passes between its star and us, it blocks a tiny part of the starlight. The star seems to dim by a tiny amount, often much less than 1%. But that dimming can be measured with sensitive tools. By measuring how much the star dims and for how long, we can figure out the planet's size and its orbital period. This is how Kate 28 billion was discovered. The Kepler Space Telescope watched the star Kate 28 for months, waiting for the special dip that meant a planet crossed in front. But the transit method gives more than just the planet's size. When the planet passes in front of the star, some starlight passes through the planet's atmosphere before reaching us. That light carries the fingerprints of whatever molecules it met. This is transmission spectroscopy, the method that detected dimethyl sulfide on Kate 28 billion. The planet's atmosphere acts like a filter, soaking up some wavelengths and letting others through. By studying which wavelengths are missing, we can tell which molecules are there. The hard part is that the signal is incredibly faint. The atmosphere of a planet like Kate Wo 118 billion is a thin layer around a fairly small world. The amount of light that actually travels through that atmosphere, instead of being blocked by the planet below, is tiny. Finding molecular fingerprints means collecting huge amounts of data and using advanced math to pull signal out of noise. This is where JWST shines. Its large mirror collects much more light than any earlier space telescope. Its infrared sensitivity lets it see wavelengths where molecular absorption is strongest. Its position at L range 2, far from Earth's noisy atmosphere, gives it a clearness impossible for ground-based observatories. When JWST observed Kate Wo 118 billion, it collected enough photons to build a spectrum detailed enough to show dimethyl sulfide. But transmission spectroscopy has limits. It only works for planets that transit, planets that pass directly between their star and us in our line of sight. Most planets do not. Their orbits tilt compared to our view, so they never cross in front of their star. For those planets, we need other methods. One option is the radial velocity method, which finds planets by measuring the wobble they cause in their star. As a planet orbits, its gravity pulls the star slightly toward us and away from us. This motion causes tiny shifts in the wavelength of the star's light, Doppler shifts, that can be measured with extremely precise spectrographs. The radial velocity method has found hundreds of exoplanets, including ones that do not transit. But it mostly tells us about mass and orbit, not about what the atmosphere is made of. Direct imaging is the holy grail. If we could simply take a picture of an exoplanet, we could study its light directly without depending on transits or wobbles. We could see continents and oceans if they exist. We could watch weather patterns change. We could look for the glow of city lights on the night side if an intelligent civilization happened to exist. Direct imaging sounds simple, but it is extremely hard. The problem is that stars are much brighter than their planets. To image a planet, you must block or subtract the starlight while keeping the planet's light. This is what coronagraphs do. A coronagraph is a device that makes an artificial eclipse inside the telescope. A small dark disk placed exactly blocks the star's light. If it is placed perfectly and the starlight is pushed down enough, nearby planets become visible. The idea is simple. The reality is very hard. Starlight does not behave politely. It bends around obstacles, spreading in patterns caused by the wave nature of light. Even a perfect coronagraph cannot fully remove starlight. Some always leaks through, making a halo of scattered light that can hide faint planets. The goal is to reduce this leakage as much as possible, ideally by factors of millions or billions. JWST carries coronagraphs made for this job. They use several masks and optical parts to reduce starlight step by step while keeping the light from off-axis sources. The result is not perfect. Scattered light still affects the images, but it is good enough to image certain planets, especially young hot planets that glow strongly in infrared. The Beta Puris system has been a top target for coronagraph imaging. The planets there, Beta Puris B and C, are young and hot, still giving off heat left over from their formation. They are bright enough in infrared that JWST's coronagraph can separate them from their star. The images are stunning, tiny points of light that are entire worlds captured from 63 light-years away. But for older, cooler planets like those in the habitable zones of sun-like stars, today's coronagraphs are not enough. The brightness difference is too extreme. The starlight blocking needed is beyond what we can do right now. This is a major reason people are building the next generation of telescopes and tools. One promising idea is the starshade. Instead of blocking starlight inside the telescope, a starshade would be a separate spacecraft flying tens of thousands of kilometers ahead of the telescope. The starshade would look like a giant flower with petals carefully shaped to control diffraction. When placed between the telescope and a target star, it would cast a shadow on the telescope, blocking starlight while letting planet light slip around the edges. The engineering problems are huge. The starshade must hold its position relative to the telescope with extreme accuracy even while separated by tens of thousands of km. The petals must be made to tolerances measured in millimeters. The opening system must unfold the shade without damage. No, starshade has flown yet, but studies continue. If the technology works, it could allow direct imaging of Earth like planets around nearby stars. Another idea is interferometry. Multiple telescopes spaced far apart can be combined to get the detail of one telescope as wide as the distance between them. An interferometer in space could possibly see details on exoplanet surfaces that single telescopes could never see. But space interferometry has its own difficulties, including the need to control the positions of many spacecraft very precisely and the hard job of combining their signals. For now, we use what we have. JWST's coronagraph and transmission spectroscopy are powerful tools. They have already produced major results. The detection of dimethyl sulfide on Kate Wo 118 billion is one of many discoveries made possible by this remarkable machine. But it is important to remember that even JWST has limits. There are planets it cannot study, questions it cannot answer, details it cannot see. The universe is huge and our tools are limited. Every telescope is a compromise between what we want and what engineering and budgets allow. JWST represents decades of work and billions of dollars, and still it can only begin to show what is out there. The gap between what we know and what we want to know is still enormous. And yet, progress is real. 30 years ago, we knew of no planets beyond our solar system. Today, we know of more than 5,000, with more found every month. 30 years ago, the idea of studying an exoplanet atmosphere was science fiction. Today, it is normal. 30 years ago, finding a possible biosignature on another world was not even a realistic goal. Today, it may have happened. The shadows are pulling back. The light is coming through. With each new tool, each new method, each new discovery, we push the darkness back a little more. We see a little more of what the universe contains. The next chapter will look at the evidence we have gathered and how heavy it is. The dimethyl sulfide detection on Kate 28 billion is exciting, but it is not proof. Science demands careful testing. Claims this big must be checked closely. What do we truly know, and what do we only guess? What would it take to move from maybe to certain? The weight of evidence is growing. The case is getting stronger, but the final decision is not yet made. The universe keeps its secrets well, giving them up only to those with the patience and the tools to look. We are looking, and slowly, step by step, the secrets are giving way. Shadows and light, the dance between what we can see and what is still hidden. The cosmic game of hide-and-seek that has shaped astronomy since the first human looked up at the night sky and wondered what was out there. The answer is coming into view one photon at a time. Chapter 8. The weight of evidence. In science, nothing is ever proven in the absolute way. Ideas are supported by evidence, and that evidence can be strong or weak, plenty or scarce, matching or conflicting. The more evidence builds up in support of an idea, the more confident we become that the idea is correct. But there is always a chance, even if tiny, that new evidence will overturn what we thought we knew. This is especially true for extraordinary claims. Finding a possible biosignature on an exoplanet is about as extraordinary as it gets. If dimethyl sulfide truly exists on Kate 118 billion, and if that dimethyl sulfide is being made by living organisms, then we have learned that life exists beyond Earth. We have answered one of the oldest and deepest questions humans have ever asked. The effects would spread through science, philosophy, religion, and every other part of human thought. Such a claim needs extreme care. It is not enough to have one detection, one signal, one suggestive result. We need confirmation. We need other explanations tested and ruled out. We need scientists to agree through independent analysis and repetition. So where are we now? What is the true weight of the evidence? The detection of dimethyl sulfide on Kate 118 billion was reported with a statistical confidence of 99.7%. That sounds very strong, and it is. But statistical confidence is not the same as certainty. A 99.7% confidence level means that if there were no dimethyl sulfide on the planet, there would still be about a 1 in 300 chance of seeing a signal that looks like dimethyl sulfide. Those odds are not tiny. Across the thousands of signals that astronomers study, false positives can happen. Also, statistical confidence covers only one kind of uncertainty. It tells us how likely the signal is to be real, based on the model we use to study the data. But what if the model is wrong? What if there are system errors in the data that we have not included? What if another molecule, one we did not think about, makes a similar spectral pattern? These are the questions that keep scientists awake at night. The dimethyl sulfide result is preliminary because these questions are not fully answered. More observations are needed to confirm the signal is real and repeatable. Other explanations must be tested carefully. The work must be checked by independent teams using different methods. The good news is that this is already happening. JWST has been given more observing time for Kate 118 billion. New data will either strengthen or weaken the case for dimethyl sulfide. Other groups are studying the existing data, looking for mistakes or different explanations. Papers are being written, peer-reviewed, and argued over. Science is doing what science does. Let us look at other possibilities. If dimethyl sulfide is not on Kate 118 billion, what else could explain the signal? One possibility is instrument artifacts. Every telescope adds some noise and distortion. These problems usually follow patterns and can be removed through calibration. But sometimes, an unexpected artifact can look like a real signal. The JWST team has worked hard to understand and remove artifacts, but unknown system effects cannot be fully ruled out. Another possibility is spectral confusion. The absorption features of dimethyl sulfide might overlap with those of other molecules. If some unexpected compound is in the atmosphere of Kate 28 billion, It might make a signal that looks like dimethyl sulfide, but is actually something else. The analysis includes known molecules, but an alien atmosphere might have chemicals we have not considered. A third possibility is that the signal is real, but not made by life. Maybe there is an unknown chemical process driven by starlight or geology that can make dimethyl sulfide without life. On Earth, we do not know of such a process, but Earth is not Kate 118 billion. The conditions there are different. The chemistry might include reactions we have never seen. This last possibility is the hardest to rule out. We can only study chemistry we know on Earth. We can model what might happen under other conditions, but models are only as good as our understanding of physics and chemistry. An alien world might have processes our models miss. The scientific answer to uncertainty is more data. If dimethyl sulfide is being made constantly by life on Kate 118 billion, it should show up in several observations taken at different times. If the signal is an artifact, it might not appear the same way each time. If the signal is real but not biological, other chemical clues might reveal what process is responsible. JWST can also search for other biosignatures that would strengthen or weaken the case. On Earth, life makes many gases besides dimethyl sulfide. Oxygen is strongly linked with photosynthesis. Methane is made by microorganisms and can build up in atmospheres. Nitrous oxide is another gas made by biological activity. If Kate 118 billion shows multiple biosignatures, the case for life becomes much stronger. If dimethyl sulfide is the only suggestive signal and other expected biosignatures are missing, that could point to a non-living explanation. The detection of methane on Kate 118 billion is interesting here. Methane is in the planet's atmosphere, confirmed by JWST. On Earth, methane is made both by life and by geology. Its presence on Kate 118 billion is not proof of life, but it fits with the idea of biological activity. Methane plus dimethyl sulfide is more suggestive than either one alone. Carbon dioxide was also detected. That is less surprising because carbon dioxide is common in atmospheres and can be made in many ways. But its presence shows that Kate 118 billion's atmosphere is chemically active, with several compounds interacting in ways that could possibly support life. What is notably missing from the spectrum of Kate 28 billion is ammonia. Ammonia is a simple molecule that should appear in a hydrogen-rich atmosphere if the chemistry is balanced. Its absence suggests that something is removing it or stopping it from forming. On Earth, ammonia is used up by microorganisms as a nitrogen source. If life on Kate 118 billion is using ammonia in a similar way, that would explain why it is missing. But other explanations exist, including destruction by starlight radiation. The weight of evidence is serious but not final. We have a dimethyl sulfide detection with high statistical confidence. We have support from methane and from missing ammonia. We have a planet that fits the profile of a Hycean world that could have liquid water oceans. We have a star old enough for life to have time to evolve. Every puzzle piece points the same way, but we still do not have proof. Proof would mean ruling out all reasonable alternative explanations, confirming the detection with many independent observations, and maybe finding other biosignatures that together make a pattern no non-living process could explain. We are not there yet. The scientific community is rightly cautious. The researchers who announced the detection were careful to call it preliminary. They did not say they had found life. They said they had found evidence that deserves more study. That difference matters. It shows the honesty science needs when facing questions this large. History teaches caution. The Mars meteorite news in 1996 created huge excitement, but the evidence did not survive close checking. The phosphine on Venus report in 2020 was first celebrated as a possible biosignature, but later studies raised doubts about the detection itself. These examples remind us that early results can be wrong, that big claims get challenged and sometimes overturned. But history also shows that sometimes big claims are true. Plate tectonics was once a strange idea, dismissed by many geologists. The bacterial origin of mitochondria was seen as ridiculous before it became accepted. Sometimes an idea that seems too wild turns out to be real. The discovery of life beyond Earth would be the most shocking discovery in scientific history. But that does not make it impossible. The next few years will matter a lot. More JWST observations of Kate 28 billion are planned. Other telescopes will add their own data. Scientists will improve models of what non-living chemistry could produce. The evidence will build one way or the other. Either the case for life will grow until it is overwhelming, or other explanations will appear that fit the data without needing biology. We are in a moment of deep uncertainty. The answer may be close, or it may be far away. We cannot know until the data arrives, but the search itself matters. The fact that we can ask this, build tools to investigate it, and push the limits of what we can know says something important about humans. We are curious. We want to understand. We will not stop until we know whether life exists beyond Earth. And if Kate 28 billion is not the answer, we will keep searching. The universe is huge. Billions of planets still need study. One of them may hold the evidence we want. The weight of evidence is growing. The balance is shifting, but the final judgment is not yet given. We wait, we watch, we study, and slowly, patiently, we move toward the truth. The next chapter will look ahead, the next steps in the search. The telescope's not yet built, the questions not yet answered, the future of our search for life among the stars. The evidence is in our hands. Now we must decide what to do with it. Chapter 9. The next chapter. The James Webb Space Telescope was built to last 5 years. It has enough fuel to run for maybe 20. But even 20 years is tiny on cosmic timescales. And the questions we are asking will not be answered by one telescope alone. The search for life beyond Earth is a project that spans generations. It will need instruments not yet built, methods not yet invented, and persistence that lasts for decades or centuries. What comes next? What telescopes are being planned? What will they be able to do? And how will they build on what JWST has started? The biggest project now being developed is the Habitable Worlds Observatory. This is NASA's next flagship space telescope, planned for launch in the late 2030s or early 2040s. Its main mission is to directly image Earth-like planets orbiting Sun-like stars and search their atmospheres for biosignatures. The Habitable Worlds Observatory will be bigger than JWST, with a primary mirror about 6 meters across. But size is not its biggest advantage. The key new feature will be its coronagraph, meant to block starlight by factors of 10 billion or more. That level is needed to see small rocky planets in the habitable zones of their stars. Today's coronagraphs are far from that goal. Reaching it will require advances in optics, wave control, and image processing that push what technology can do. If the Habitable Worlds Observatory works, it will be able to take spectra of Earth-like exoplanets, checking their atmospheres for signs of life. Imagine looking at a planet like ours orbiting a star like our Sun and detecting oxygen, methane, water vapor, and maybe dimethyl sulfide or other biosignatures. Imagine confirming that another world has an atmosphere shaped by life. That is the goal. The technology challenges are huge. The telescope must be extremely steady, with vibrations measured in picometers. The coronagraph must block starlight with record-breaking power. The detectors must be sensitive enough to catch the faint glow of a planet 10 billion times dimmer than its star. Each requirement pushes the best technology farther than ever before, but NASA has committed to the project. A study phase is underway. Engineers are designing parts and testing ideas. The road to launch is long and uncertain, but the goal is clear. A telescope that can find life on other worlds. A machine that could answer our oldest question. While we wait for the Habitable Worlds Observatory, other projects will keep searching. The European Space Agency is building Ariel, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, planned for launch in 2029. Ariel will study the atmospheres of about 1,000 exoplanets, creating a wide catalog of their chemical makeups. It will not be sensitive enough to find biosignatures on Earth-like worlds, but it will give important context for understanding atmospheres in general. On the ground, a new generation of extremely large telescopes is being built. The Extremely Large Telescope in Chile, the 30-meter telescope in Hawaii, and the Giant Magellan Telescope also in Chile, will each have mirrors far larger than any current telescope. Ground-based telescopes cannot match space telescopes for some work, but they have advantages like huge mirrors and the ability to upgrade instruments over time. These giant telescopes will use adaptive optics to correct for air distortion, reaching sharpness close to what space can do. They will study exoplanet atmospheres through transmission spectroscopy, adding to JWST's work, and their huge light collecting power will allow them to study fainter, farther targets. The mix of space and ground tools creates a teamwork stronger than either one alone. Space telescopes give the steady, dark setting needed for the most sensitive work. Ground telescopes give the massive mirrors needed to collect enough light for detailed spectroscopy. Together, they form a network of instruments, each adding its strengths to the shared goal. Beyond telescopes, other technologies are being built that could change the search for life. Starshades, as mentioned earlier, could allow direct imaging of exoplanets that today's coronagraphs cannot reach. Space interferometers could combine light from several spacecraft to achieve detail impossible for any single telescope. Even stranger ideas, like using the sun's gravity as a lens to magnify distant objects, have been suggested for the far future. The search is also reaching beyond our nearby stars. The closest stars are easiest to study, but they are only a small part of the galaxy. New surveys are finding planets around stars thousands of light years away. Studies of exoplanet populations suggest that Earth-like planets in habitable zones may be common, maybe in the billions across the Milky Way. Most are too far for detailed atmosphere studies with today's technology, but future tools may change that, and surprises are always possible. Science moves forward not only through plans but through unexpected discoveries. A new method, a strange signal, a result nobody predicted. Astronomy is full of surprises. Pulsars, quasars, and exoplanets themselves were found when observers saw something they were not expecting. The next big breakthrough may come from a direction we cannot guess. What would it mean if we confirmed life on Kate 118 billion or any other exoplanet? The first scientific effects would be enormous. Biology would need to include life that evolved separately from Earth. Chemistry would gain new examples of how living-like processes can work. Astronomy would shift from finding possibly habitable worlds to studying worlds that are truly inhabited. The philosophical effects would be just as big. For thousands of years, people have argued about whether life is rare or common in the universe. Religions, philosophies, and cultures have all wrestled with this question. Confirming alien life would force us to rethink our place in the cosmos. We would not be alone. We would be part of a bigger story that includes other living things, other histories of evolution, and other ways of being. There could also be practical effects, though they are harder to predict. Learning how life began and changed on another world could help explain our own origins. The chemistry of alien life might suggest new ideas for medicine, farming, or industry. Even knowing that life is common could change how we think about our future, our duties to other species, and our long-term survival as a civilization. But those are thoughts for another day. Today, we are still collecting evidence. The dimethyl sulfide signal on Kate 28 billion is an exciting hint, not a confirmed discovery. More work is needed, more observations, more analysis, more checking. Science moves slowly and carefully on purpose. Big claims need big evidence, and we are still building that evidence. The next few years will be crucial. JWST will keep watching Kate 118 billion and other promising targets. Data will build up. Patterns will appear or not. The case for life will grow stronger or weaker. And someday, maybe within a decade, we may have an answer. Or maybe it will take longer. Maybe Kate 118 billion will stay unclear, and the clear detection will come from another planet seen by a future telescope that does not exist yet. The search may last across generations, with each generation adding evidence, improving methods, and building better tools. Either way, the search will continue, because the question is too important to drop, and curiosity is part of who we are. Because we cannot look up at the stars and not wonder. The next chapter of this story is not written yet. It will be written by the scientists and engineers who build the next telescopes, by the astronomers who study the data, by the theorists who explain the results. It will be written by everyone who cares about this question and helps in whatever way they can to find the answer. The search for life beyond Earth is humanity's quest. It began when the first person looked up at the night sky and wondered. It continues today with tools of amazing power aimed at distant worlds. And it will continue into the future as long as humans stay curious. As long as we keep asking questions, and as long as we refuse to accept not knowing when knowledge is within reach. The next chapter is coming. We do not know what it will hold, but we know we will be there to read it, to learn from it, and to be changed by it. The universe is huge and full of secrets. We are learning to uncover them one discovery at a time. Chapter 10. The question that changes everything. 120 light-years away, a planet orbits a red dwarf star. The planet is wrapped in hydrogen, warmed by dim orange light, and may be covered by an ocean deeper than any on Earth. Somewhere in that ocean, or floating in that atmosphere, something may be alive. Something may be using sulfur compounds for energy and releasing dimethyl sulfide into the alien sky. Something may be the answer to a question humans have asked since the beginning. Are we alone? For most of human history, that question could not be answered. We could guess. We could imagine. We could tell stories about gods and spirits and beings from other worlds, but we could not investigate. The stars were points of light, unbelievably far away, completely out of reach. Whatever was out there was beyond our knowledge, beyond our tools, beyond our grasp. That changed in our lifetime. In a single generation, we went from knowing nothing about planets around other stars to knowing thousands. We built telescopes that can study the atmospheres of worlds 100 light-years away. We built machines that float in the darkness of space, collecting old photons and reading the messages they carry. And now, for the first time, we have evidence that suggests we may not be alone. Evidence that is preliminary, that needs confirmation, that might still be explained away, but evidence all the same. A molecule that on Earth is made only by life, found in the atmosphere of a world that could support life. If the detection is confirmed, what changes? Everything changes. The discovery of life beyond Earth would be the biggest finding in the history of science. It would show that life is not a fluke, not a one-time accident on one lucky planet. It would show that life is a process, a tendency of matter to organize into self-copying patterns wherever conditions allow. It would suggest that life is common. Across the universe, every star we see might have worlds, and some of those worlds might have biology. This changes how we see ourselves. For thousands of years, humans have believed, or at least hoped, that we are special, made in the image of a god placed at the center of the cosmos, unique among all beings. Finding alien life would challenge that belief. We would no longer be the only living things in the universe. We would be part of a vast community of life, one species among possibly billions, spread across galaxies too many to count. Some might feel humbled, some might feel afraid, but others would feel inspired. Because if life is common, then the universe is not a cold, dead emptiness. It is alive. It is filled with existence. Every star we see is a possible home for beings we cannot imagine. The cosmos is not empty. It is full. This changes how we think about our future. If life exists on Kate Wo 118 billion, it probably exists on many other worlds too. Some of those worlds might have intelligent life, civilizations that built technology, built cities, and asked their own questions about the universe. We do not know how common intelligence is. We do not know whether any civilization lasted long enough to communicate across the stars. But the existence of simple life would make complex life more possible. And that brings more questions. If intelligent life exists elsewhere, why have we not heard from it? This is the Fermi paradox, named after the physicist Enrico Fermi, who reportedly asked, "Where is everybody?" If the universe is full of life, there should be signs, radio signals, mega structures, something. The silence is strange. Maybe intelligence is rare, even if simple life is common. Maybe civilizations destroy themselves before they can spread through the galaxy. Maybe they exist but choose not to talk. Maybe they're talking in ways we have not learned to detect. Finding life on Kate Wo 118 billion would not solve the Fermi paradox, but it would sharpen the question. If life exists 120 light-years away, why does the universe seem so quiet? This changes how we think about responsibility. If life is precious, if it appears rarely and survives with difficulty, then we have a duty to protect it, not only on Earth, but wherever it exists. Finding alien life would create new ethical duties. We would have to think about how our actions affect other living beings, even on distant worlds. We would have to think about contamination, about the risks of exploration, about the rights of non-human life. These are heavy questions. They touch philosophy, religion, politics, and law. People would debate them for generations. The discovery of life beyond Earth would not just be a scientific moment. It would be a turning point in human civilization, the moment we learned we are not alone. But let us step back from the huge meanings and return to the present. The present where we have evidence but not proof, where the dimethyl sulfide signal is suggestive but not final, where scientists are still gathering data, still studying results, still debating meanings. This is how discovery works. It does not happen in one instant. It happens in steps. First a hint, then more data, then confirmation or rejection, then understanding. The process takes time. It needs patience. It demands honesty, the willingness to follow evidence wherever it leads, even if it leads somewhere we did not expect. We are at the beginning. The hint is there. The molecule has been detected. The model says it could mean life, but we do not yet know for sure. The universe has not revealed its secrets. It has only shown a tempting glimpse. What we do with that glimpse matters. We could ignore it, calling it noise or wishful thinking. We could overread it, claiming proof when there is only suggestion. Or we could do what science requires. Investigate, gather more data, test hypotheses, and seek the truth, whatever it turns out to be. The search continues. JWST is still observing. New telescopes are being built. The next generation of instruments will be stronger, more sensitive, and more capable than anything we have now. If life exists on Kate 118 billion, we will learn. If it does not, we will look elsewhere. The question is too important to drop. And so we come to the end of this story, though it is not truly the end. It is a pause, a moment to think about how far we have come and how far we still must go. 100 years ago, we did not know other galaxies existed. We thought the Milky Way was the whole universe. 50 years ago, we had not walked on the moon. 30 years ago, we knew of no planets beyond our solar system. Discovery is speeding up. Each decade brings findings that change how we understand the cosmos. The dimethyl sulfide signal on Kate 28 billion might be the next great finding. Or it might be a false alarm, a signal that looked hopeful but did not hold up. We do not know yet. We cannot know until the data is collected and the analysis is finished. But either way, the search matters. The act of looking, of building tools and aiming them at the sky, of asking questions and seeking answers, is what makes us human. We are curious, we want to understand. We will not stop until we know what is out there. Kate 118 billion drifts in the darkness 120 light-years away. Its hydrogen atmosphere swirls above whatever surface lies below. Its red dwarf star gives dim light across an alien landscape we can barely picture. And somewhere on that world, something may be living. Something may be breathing. Something may be waiting to be found. We are coming with our telescopes and our spectrographs and our endless curiosity. We are reaching across the light years, collecting photons and decoding signals. We are searching for the answer to our oldest question. Are we alone? The universe is starting to answer. The molecule of life has been found on a distant world. The evidence is building. The weight is growing. Maybe soon we will know. Maybe within our lifetimes the question will be answered. And when it is, everything will change. But even if the answer takes longer, even if it comes in the next century or the one after, the search will still matter. Because the search is who we are. It is what we do. It is the best of humanity, our curiosity, our courage, and our determination to know. Look up at the stars tonight. Find the constellation Leo. Somewhere in that direction, too faint to see with your eyes, is a red dwarf star with a planet that may hold life. That planet is real. The evidence is real. And for the first time in human history, we have the tools to investigate. This is the question that changes everything, and we are close to answering it. The universe is vast. The darkness is deep. But we carry light with us wherever we go, the light of knowledge, the light of understanding, the light of discovery. We are not alone in our search. Billions of humans share this world, this time, this question. And maybe across the light years, other beings share it too, other minds looking up at their own stars, wondering if anyone else is out there. If they are, we will find them or they will find us. Either way, the universe will never be the same. Thank you for joining me on this journey. If you enjoyed this deep dive into the search for life beyond Earth, please like and subscribe. Tell me in the comments what you think. Is the evidence convincing? Are we alone? And what should we explore next? The moons of Jupiter and Saturn have their own mysteries. The atmospheres of Venus and Mars may hold surprises. And every day new planets are discovered. New questions are raised. New possibilities emerge. The search continues. The question remains, and the answer, when it comes, will change everything. Until next time, keep looking up, keep wondering, keep searching. 0.